Welcome back to Max Repair. As always, hit the like, share, subscribe. It helps me out. I appreciate that. I am standing here today with a 352 Ford. This is an FE family of engine. I actually have quite a bit of videos that I'm doing on this engine, the full teardown. This one is going to be the measurements and then potentially the reassembly. At least I hope we get to the reassembly. So there's a pretty long series that will go with this. And there is also some videos on the 1965 F250 that has been in one family its entire life that this engine goes to. So, as I kind of already said, today I'm going to be measuring this engine to decide what it's going to take to rebuild it. This was a running engine when the transmission decided it wasn't going to work anymore. Um, so that was probably about 15 years ago at this point, and it has sat ever since. Now, I've already done like one cylinder measurement on this thing, and I already kind of know where we're going to be at, but I'll walk you through what bore taper is, what outer round is, and all that stuff, and thrust and non-thrust sides of a piston. So, this will be fun and informative, and at the end I will measure this engine up and we will have to kind of decide what we're going to do with it. Although I kind of already have. I'm just going to walk you through the process as well. So I'm going to go ahead and start with showing you the specs that I've got on this engine. The only one I couldn't really come up with very well was the 4-inch bore. It's got a 4-inch bore. Tons of engines use a 4-inch bore. It's very common in V8s. Just off the top of my head, we've got this 352 Ford. Also in the family of Fords is the 351 Cleveland, the 351 Windsor. Don't really know about the 351M, but that engine is garbage and it doesn't matter. Chevy, we had the 350, 327, 302. Chrysler, I believe the 360 might be the only one. There's also a 361 big block. It might have a 4-inch bore, but I'm not really sure. There might be a big block with a 4-inch bore, but I don't know for sure. In fact, I'm pretty sure that 361 is not a 4-inch bore because it should have the B series crankshaft, which would make it not that. Anyway, so 4-inch bore is pretty common. So let's start out with the specs that we've got for this engine. The bore spec, I'm not 100% sure that's right, but I'm fairly certain it is. And honestly, the taper and outer round are going to be kind of the bigger issue. And realistically, that number is kind of set by the pistons you use if you're going to buy a set of aftermarket pistons and maybe bore this engine, which we'll get to in a little bit. So we'll start down at the bottom. The bore we're going to say is 4.000. That is 4 inches exactly. I have things largely measured out to the thousandths, although a lot of specs went to the 10,000 spot. I don't know that I have accurate enough equipment to really pull that measurement off, but we'll give it a shot. Taper is something we're going to have to worry about, which is, I'll get to what that is here in a minute. We've got 1/1000th of an inch for taper, 1/1000th of an inch for outer round, and up top, this kind of matters, we have anywhere from 15 10,000ths to 23 10,000ths. All these are in inches as well, of clearance between the piston, skirt, and the cylinder wall. Let's see here, Rod Journal. Yeah, just read it. I am not going to try to say those because I will screw them up. That's our tolerances, though. Basically 2 3/4. Real close. Those are the main journals. The Rod journals are, again, right there. You can read them. So those are the specs on this 352 as I have found. Now, I'll kind of show you this stuff as we go. Sometimes just having this as an idea of how much you're going to have to machine is kind of a starting point. All right, I'm going to do the best I can to, oh, maybe I can do this. Might work. Okay, so here's our cylinder. Here's our piston. crankshaft goes around. As it does that, the rod moves. I'm probably not getting the rotation right, but anyway, you get kind of the idea. The thrust side of a piston is the part that gets shoved into the block as it is moving down. So when the rod is straight up and down, which happens twice per revolution, there is no thrust on it. But anywhere else, when there's being force put on the piston, it is shoving the piston either to the side. I'm losing the camera. Okay. It is shoving the piston either this way or this way, and that causes an accelerated wear. So, when we look at our block, the crankshaft comes down through the center, like right there. It's not in there. So the thrust side is going to be like this. This will be the thrust angle of the cylinder. The non-thrust is going to be here because the connecting rod should not be putting any pressure this way. Should be putting pressure this way. Now what that means typically is your piston or your cylinder walls will generally have more wear on the thrust side than they do on the non-thrust side, and you can see on this piston skirt there's some scraping, and that's because the piston's been basically jammed against that cylinder wall on that side. Okay, so that's thrust and non-thrust. Now I drew these up. You're going to have to kind of bear with me. I'm not an artist or a drawer. But let's take a look at the thrust side taper wear first. This would be something that's probably a bit exaggerated, but very possible. Now, I drew these using a whatchamajigger, so they're actually straight lines. But in a lot of cases, they'll actually be kind of curved. So they'll go basically straight up to maybe halfway up, and then they kind of curve out, and the farther up they are, the bigger the bore gets. But that is that's fine for this illustration, or for this example. This is going to do just great. So if we have our bore size that started out at 4.004 inches exactly, and we have an engine that has a ton of wear, you may have something that has 10 thousandths of an inch wear at the top. So if you have that, you have 4 and 10 thousandths of an inch at the just below that. But you'll actually typically have right at the very top, where the rings don't run to, the standard bore size. So you'll have this little area that's normal size, and then probably like 1/8 of an inch down into the bore, you have this very wide wear. And I drew this relatively even, but you have also within thrust what is called the major thrust and the minor thrust, and this will actually be wore like sideways most of the time, and it depends on what side of the engine it's on and which way the rod is laid when it is making power, when your power stroke is happening. So in this, even though this is 10 thousandths out, it may be like 2 thousandths here and 8 thousandths over here. That'd be pretty extreme. It probably wouldn't be that much, but it might. Then as we go down through the middle, we might only have 3 thousandths of wear, even though we started at 10. And down at the bottom, generally the bottom where the piston rides is very close to where it started life. Now on the non-thrust side, that's going to give you maybe and again, these are just theoretical numbers, but stuff I'm throwing out there. Maybe you have 6 thousandths of wear at the top, that same 3 thousandths in the middle, and we're back down to standard at the bottom. So if we are at the top and we have 10 thousandths wear on the thrust direction and 6 thousandths wear on the non-thrust direction, if we subtract 6 thousandths from 10 thousandths, that means that we also have 4 thousandths of outer round. I've got a worksheet that goes with this, and I'm actually going to share it with the video. So if you want to look through this stuff and use some of what I'm showing you in your own engine, I'm giving you the materials to do that. Now, this is just by me running my finger up the bore, and I can kind of feel what's going on. this FE feels really weird. In fact, I can't say that I've ever felt another engine that feels quite like this, but I've also never rebuilt any other FEs. So what this FE has is, like, as it comes up, it comes to its widest point, then it bumps in, comes back, gets a little wider again, and then there's a ridge. So that's going to be super hard for me to measure with the tools that I have. So I'm going to end up measuring more down here at its largest point. So this one feels weird, and maybe you can already tell by the drawing here that this engine is probably going to need bore work, and I could tell that just by running my finger up. The way it felt let me know that this thing is probably out of spec. Okay, I haven't even started editing this, and I know it's going to be like a 25-minute video. So if you're sticking with me through the whole thing, you must actually want to know how to do this. I'm going to show you how to use a snap gauge and a micrometer. That's all I'm going to use on this. If you had a bore gauge, that would be better. Personally, I don't use them enough to be good at them. A lot of this measurement stuff, the more you do it, the better you get. And at one point, I was super accurate with a snap gauge and a micrometer. Probably not so much right now because I haven't done a lot of engine work or a lot of precision measuring in a while. But I'm also not going to teach you how to read a micrometer. You'll have to do that on your own. So I'm going to go ahead and get started. I'll pull the camera over. Actually, before I get started, let me show you the worksheet. Alright, so this is the first page of the worksheet. We got cylinders 1 through 3 plus instructions, and then cylinders 4 through 8 on the second page. So I'll go ahead and kind of read you the instructions here. This worksheet provides a place for you to track the measurements made on the engine block, specifically the cylinders. A total of 6 measurements will be taken in each cylinder. They will be taken at the top. Ooh, man, I got a typo in there. That's all right. Top of ring travel, mid-cylinder, and at the bottom of... Dang, 2 typos on the same word. All right. And the bottom of ring travel. Measurements will be taken on the thrust side and at 90 degrees to the thrust side. So I've used this worksheet in high school classes probably, I don't know, I did it for 14 years and I used this every other year, so I probably used this 7 times and nobody told me I misspelled ring twice. But anyway, so our cylinder bore spec, I'm just going to go ahead and fill that out right now. It's going to be 4.000 inch, and then a lot of the time you would put a plus minus, maybe it's 0.001 thousandth of an inch. Okay, so now we're going to go ahead and I'm going to start on, I guess I can do cylinder number 1, but we'll go ahead and measure the thrust angle, or the measurements. So what I'm going to do is I'm going to take a measurement here. This is going to be the top of the thrust angle, middle right about here, and then you can kind of see, I'm not sure how well it's going to show up for you, but I can see the bottom of ring travel is right about there. So I'll also measure right at the bottom of ring travel. Then I'm going to come over and do top, middle, bottom. And depending on what you find, you may adjust your measurements after one cylinder. And I'm actually going to do it on number 7 here because I think this is the worst one. Sometimes you'll be able to just kind of tell. I'm pretty sure this cylinder, which on this Ford is number 7, I think that's going to be the worst cylinder on the motor. So I'll start there. I'll video it, show you what I'm doing. Okay, so I'm starting off with my snap gauge closed. I'm going to bring the bottom one up to where I want to actually measure. Open up my snap gauge, kind of center it. I don't have it level right now. What I have is like pretty angular. So then I've got the snap gauge locked in. I'm going to rotate this up. Okay, and as it rotates up, I'm going to get to the point where the top part is right about the end of that travel. Then I'll go ahead and roll this through. And what that's done is just shrink this down to the size of the actual bore. Now I'll grab my micrometer and I'm going to just straight up measure between there. Okay, so this one has a nice digital readout. It is like right between 7 and 8 thousandths over 4 inch. So we'll call that, I don't have the accuracy measurements. Oh, actually I do. So if I look at the 10,000th spot, this is 6 10,000ths. So the top thrust is going to be 4.0076. Okay. So now I'm going to take this same thing. I'm going to go about the middle of the cylinder. Do the same exact thing. Drag it through. Okay. I'm expecting this to be a little bit smaller. And it is. This is 3,000th over 4 inch. So that's going to be 4.003. I'm not going to worry about the 10,000ths there. And then at the bottom, we're going to do it again. And then at the bottom, I got 2,000ths. So 4.002. Okay. So we'll start at the top again. That can't be right. Maybe. I'm going to check that again because I got 4.001 or 1,000th over 4 inch, which seems unlikely. Okay, I just got, well, I got 5,000ths. Yeah, I might just be terrible at this. So I'm pretty consistently getting about 4.5 thousandths over on that one. We'll call it 4.6 instead of 4.5 because math is going to be much easier if I do that. Alright, so now time for math equation stuff. You're going to take your bigger number, subtract it from your smaller number on this line, and we're going to get 0.003, so 3,000ths of an inch difference. This was actually a 4.5. I just made it a 4.6 because I didn't want to do the hard math, and it doesn't really matter. In the middle, we've got 2,000ths difference. And at the bottom, we've got 1,000th difference. Now, taper-wise, we take the biggest number, which is probably going to be the top, and subtract it from the bottom. So, let's call this 20 because we went too far on that one. So, we'll subtract... So 5.5 thousandths of taper on that side, and then we'll do the same thing. And we've got basically 3.5 thousandths of taper on the non-thrust. So this is pretty standard, and I actually didn't write all this stuff down. All I really did was measure this and this. And thought, oh man, this thing is in terrible shape. It's going to need board. Because the maximum allowable amount of taper was 1,000th of an inch. the maximum allowable amount of outer round was 1/1000 of an inch. So basically that. So we failed on outer round with 3/1000 of an inch, and we failed on taper with 5.5 of an inch. So pretty wildly out. Now, there are some things, if you're really, really budgeting and trying to figure out how to do this, this one is probably too far gone, but somebody that's really good at honing could maybe straighten out 3/1000. And then there's a deal where you can knurl pistons, although I don't know where you would find to actually do that anymore. It used to be a common practice. So you could maybe make something that's a little bit big work without boring. But after measuring just this one cylinder, I know we're going to have to bore this engine. And based on that measurement, we might be able to get away with 20,000th overbore, but chances are we'll end up going 30. So all I'm going to do is take this top thrust angle measurement on the rest of the cylinders. And the reason I'm going to do that is because I want to have an idea where we're going to be able to go bore-wise. So yeah, I'm going to measure that. You're not going to watch me. I'm just going to do it, and then I'll show you what I come up with. All the measurements are taken. Well, not all. I did the important measurements because I did this whole cylinder, so I know we're in trouble. So I just did what should be the biggest measurement in the engine. So cylinder 1 was 5/1000 over the 4-inch, 3.5/1000, 5/1000, 4/1000, 6/1000, 6/1000, and 8/1000. So cylinder 8 was maybe a touch worse than cylinder 7, but I didn't measure all the other stuff because we know it needs bore work. So I'm not going to worry too much about it. Alright, so that's it for the yep. Now we are going to move on to the crankshaft. I also have a worksheet for this. So I'll read you the directions real quick. Crankshaft. In measurements, front refers to the front of the crankshaft or balancer end of journal. Rear refers to flywheel end. And then I have this main specs and rod specs right up there at the top. Then I have all your main journals listed out. Another page where it goes to rod journals. The journal number refers to the position of the rods from front to back on the crankshaft. This will follow Chevy and Chrysler cylinder numbering, not Ford. Front and rear designation is the same as the mains. Alright, so let me explain that for Ford. Okay, so you can see this is this groove here is not actually a groove, that's oil buildup. So this is the front of the crankshaft where the balancer would ride. This is our main journal, main journal, main journal, main journal, main journal. Now that leaves rod, 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 rod. Okay, so this is a V8 type engine. It only has 4 rod journals. The rods, and in most V-type engines, this will be the case, also the case in flat engines, they will share a rod journal with 2 pistons. So this is the farthest forward cylinder, this is the next cylinder. So if you have a Chevy or a Chrysler, cylinder numbering would be cylinder number 1, cylinder number 2, cylinder number 3, 4, 5, 6, 7, 8. Okay, so it just goes front to back and the numbers go with the position on the rod. Ford does it different. So if we look at, and the reason I specify this, and you can do it however you want. I used to teach classes with this and I wanted to know what I was looking at and I wanted them to do it in a structured way. But this is going to be on a Ford, cylinder 1, 5, cylinder 5, so 1 and 5 share a journal. 2, 6, 3, 7, 4, 8. Okay, so yeah, I'm not a huge fan of how Ford numbers their stuff, but as long as you're aware of it, you can adjust and compensate. Okay, so kind of the same deal here. You probably can't see it, but these are scratched and grooved pretty heavily. In fact, I'm almost positive you're not going to be able to see it on camera. But regardless of what these measure, this crankshaft is most likely not going to polish out, which would be just kind of to run some very fine grit sandpaper and polish these journals smooth. This is going to, so I can catch my fingernail pretty aggressively as I scrape it along here. That means that we have a couple thousandths of wear. So this thing needs to be what they consider turned, or the journals smallened up. So I'm going to take just a quick measurement. The right way to do this would be to use a micrometer. The way I'm going to do this right now is just with a pair of calipers. Okay, so this is the main journal. Oop, I got to put this thing down. Main journal, measurement 1. Okay, so I got, and that's not quite right, but I'm fine with it. So position 1 was a 2.750. Okay, so that was this way. What I would then want them to do or want you to do to check for out around is to come in and measure this way. Okay, so we're gonna come in here and measure. I'm gonna dangle it off the side. And I didn't suspect this thing had been turned. And it looks like it has not, because I just came up with 275 again. Alright, so that was the main front. That's all I'm going to worry about. So I would do measurement here, then I would move to the back side of the journal, do a measurement there. So we would take 4 measurements on each journal. That's not, I'm not super worried about it on this one right now, because this thing needs work. Okay, same thing with the rods. I'll kind of clean this one up a little bit. Not as worried about keeping it clean right now, because I know it needs, when it comes back from machining, it's going to need to be cleaned really thoroughly. So, God, I keep screwing up the measurements. So that's not it. That's bigger than stock. So hold on. Let me try this again. 2.437 is like right there. So okay. So again, same deal on this rod journal here. I would actually take 8 measurements, but for this particular engine, that's all I actually need to measure, because it tells me where I'm at, and I know this thing needs crank work just by, well, by experience, by looking at it. This one here is really bad. Ooh, boy. Okay, so this spot right here is grooved super deep. I don't even know if that's going to come out at a 10,000th cleanup. The crank person will let me know if that's okay. I somewhat expect this to come back with the rest of the journal super nice, and still a little bit of a groove in what would that be? 1, 2, 3. The number 3, which also happens to be our thrust journal. So yeah, now we've got our measurements, and it's pretty apparent to me that in the case of this engine, it really needs to be machined to make a good running engine when we're done with it. Now this is the kind of thing that it probably ran okay before, and it's been 15 years, so he's not going to notice the difference. In fact, if anything, the regular car that this guy drives is probably so much faster than what he had 15 years ago that this will probably actually feel worse. But if you were to go one day from this as a running engine to what we're going to do, it would be unbelievable how much better the new engine runs. Unfortunate for him that it's been many years, and regular cars are way faster and way better than they used to be. So this will actually probably feel slower than he remembers it. Now, on to the weird taper part. So along with the weird taper, not every single, 6 out of 8 pistons came out with broken top rings. Now, I haven't actually measured this, but I believe this bottom ring looks to be a little bit thicker than the top, and I think that may play a factor in this. Where did I put my majigger? There it is. This is not really precise enough to do much, but it'll get this point across. So this is 755 thousandths. Yeah. Yep. Alright. So when I measure it, this ring, and I don't know what this creates in a fraction, but this is basically 75 thousandths of an inch. Okay? This one is basically 925 ten thousandths, or we'll call it 93 thousandths of an inch. So we got 75 thousandths to 93 thousandths. The thing that causes your engine to wear realistically are the rings. So if you look at an old engine, which this is, it's a 1965, the rings used to be much thicker and heavier. So they would press out, and the rings are what generally wears the engine out. That and the fact that there is an explosion on top of this piston, which jams the rings into the cylinder walls a little bit. Now, what most people don't realize about a gas engine is that pretty much all your explosion is used up within the top, like, 3/4 of an inch of travel, and it actually varies depending on how wide open or closed your throttle is. So at an idle, your actual high pressure area in the piston might be so minuscule that it's hard to even measure. Obviously it does something because it's enough to run that engine through the next 3 3/4 cycle, but it is that's what happens, is the rings and the explosion. The explosion is why it wears more at the top, and the rings don't go all the way to the bottom, which helps the bottom stay a little bit better. The heavier the rings, the more it wears. I think, and I don't have anything to back this up other than what I think. I think this heavier ring on the bottom puts more pressure out and actually causes the engine to wear. And then as this thing gets old, it creates 2 ridges in the engine. So you've got the upper ring ridge and the lower ring ridge. And I think that's because it's got a lighter ring on top that just doesn't wear as much. And as it's running, that lighter ring ridge creates a shelf for this top ring to jump over and ends up breaking it. And then once it breaks, then you really start to have some weird wear in that cylinder. So that's what I think is happening, but I've got nothing to back that up other than what I think is happening, and the fact that I probably have at least an okay amount of knowledge about automotive engines. So that's my theory on why this thing is wore out weird, and my guess is that most FE engines will be wore in a very similar way, or engines that have a thicker second ring like this one does. I think that's it. I wanted to do cylinder head measurements. I could do deck measurements, but to be real honest, the deck on this thing is pretty nasty. It's going to get real well cleaned at the machine shop, and it's a machine shop that I don't personally have experience with, but several of my friends do, and everybody's been very happy. So I'm going to go ahead and trust that guy's going to do some pretty good work. Trust and verify. So when I get it back, I'll measure stuff before I put it back together. In fact, this little measurement series here was just kind of deciding what's going to be the machine work process. When we get it back, I will fill out both of those sheets 100% to make sure everything measures out. and then we'll put it back together. And I will actually do more measurements than that. Like we'll measure the pistons, make sure they're going to be fit for the cylinder, which the machine shop is going to do. I'm gonna go right through this though. Not sure if I'll make a video on that or not. I probably will. So that said, thanks for watching. Hit the like, share, subscribe. I appreciate it. It helps me out. And you could probably be wasting your time more aggressively than watching this. It can't be the worst channel on YouTube. There's no way it's the worst. Probably not the best either, but can't be the worst. So that's it. See you later.